Good morning again. We discussed elastic properties. We're doing thermal expansion. We'll finish that today, and we'll start thermal conductivity. So these are some of the properties that are important to manipulate to get improved thermal shock or refractories. So the basic idea here, I'm going over these properties. They're pretty much fixed. If you have a dense ceramic or refractory, fine crystalline size, these properties are pretty much fixed. So you have to change the microstructure to accommodate better thermal shock resistance. So that's why we're going over all of these properties. So we left off on thermal expansion. I was going over some typical values of thermal expansion for different types of fired refractories. And this table pretty much, or figure pretty much summarizes the thermal expansion for a whole range of refractory materials. So we have linear expansion versus temperature here in degrees C, goes up to about 1600 degrees C, and it's just 2.5. So at the top of this diagram are the MgO-based materials, the MgO and chrome-based materials. They have the highest expansion. In the middle of the diagram are the alumina-silica refractories, and towards the bottom are the non-oxides, and then there's the few unusual low expansion materials at the very bottom. So the basic refractories on this chart are 2, 3, 4, 5, 7, and 8. And if you look at these, the thermal expansion decreases with decreasing MgO content. So 2 is about a 98% MgO material, but as you go down, the MgO content decreases and the thermal expansion decreases. So again, MgO is one of the highest thermal expansion refractories there is. In the middle of the diagram are the alumina-silica refractories. These are 9, 10, 11, 13, 14, and 15. So 9 is a 99% alumina. And as you decrease the alumina content, going in the downward direction, the thermal expansion decreases. So the Super Duty fire brick, like 15 down here, they would have much lower thermal expansion than the high alumina materials. So thermal expansion decreases with alumina content. And then the non-oxide materials like silicon carbide and silicon nitride, 16 and 17, they have the lowest expansion coefficients compared to the oxides. And then these unusual low expansion materials, 19 is the fused silica we mentioned, 18 is cordierite, and 20 is spodumene. So unfortunately, especially 19 and 20, very low expansions, but they have very low use temperatures. And the fused silica, again, crystallizes to cristobalite, usually above about 1200 degrees C. So this chart describes a whole range of refractory materials, and I have a table here for reference. We'll just look at a few. MgO and CaO, 14 and 13 times 10 to the minus 6, and that's per degree C. And these are from room temperature to 1000 degrees C, so they're average values. So these are the higher thermal expansion materials. CrO2 is still pretty high, 10. Phosphorite is a magnesium silicate, that's about 9.5. You can see graphite is pretty low, around 4. Cordierite is only 2.7, but that's a low temperature material. And your carbide and your nitrides are around 5 and 3. And the common material, aluminum oxide, is about 8.6. So from about 3 to 14 is the range, times 10 to the minus 6. That's the range for refractory materials. So the lower the expansion, the better chance you have of making a material that has thermal shock resistance. So we'll look at different things that affect the thermal expansion, and we'll start out with phase transformations. Um, when you have a crystal phase transformation, you have a volume change. Volume changes lead to microcracking, and perhaps even a more serious situation where you have catastrophic failure. So when you have these volumetric changes, they decrease the strength because they create microcracks, which are flaws. But they increase the thermal shock resistance. So when microcracks form, they dissipate the stored elastic strain energy, which is the driving force for fracture. So microcracks dissipate stored elastic strain energy due to the thermal stresses by creating the new fracture surfaces. So you convert stored elastic strain energy to fracture surface energy. So microcracks hurt the strength, but they improve the thermal shock resistance. So there's two types of phase transformations. There's a displacive transformation and a reconstructive transformation. So this is a normal, well-ordered crystalline structure. When you go through a displacive transformation, either B or C, either one of these diagrams, you're just distorting the crystal structure. So you're changing bond angles. You're not breaking and reforming bonds. You're just changing the angles, and it's a very rapid transformation. The other type is the reconstructive transformation. That's diagram D. Now you break atomic bonds and reform bonds, and you're really making a different crystal structure. So that type of transformation is sluggish. It's a slow type of transformation. But either type of transformation has a volume change associated with it. And one of the materials that exhibits a great deal of these transformations is SiO2 silica. It exhibits both the reconstructive and the displacive phase transformations. So there's three crystalline forms: quartz, tridymite, and cristobalite. If you start out with quartz, it has a displacive transformation at 573 degrees C to high quartz. So it goes from low quartz to high quartz. There's a 0.9% volume expansion. If you have tridymite, you go through two displacive transformations, one at 105 degrees C and one at 160 degrees C. So you go from low to middle to high tridymite, and that has a 0.5% volume expansion. And then cristobalite goes from low to high cristobalite around 200 to 270 degrees C, and that's a 2.8% volume expansion. So when you start out with quartz to manufacture a silica refractory, you want to convert the quartz to either high tridymite or high cristobalite. So you have to go through these reconstructive phase transformations. So when you convert quartz to tridymite, thermodynamics predicts transformation at 867 degrees C, but that doesn't really happen because of the kinetics are too slow there. So it's more realistic around 1400 degrees C. You can convert quartz to tridymite, but there's a 14% volume increase. And if you go to a higher temperature, 1470 degrees C, you can convert quartz to cristobalite, but that's a 17% volume increase. So any of these changes in volume can create micro cracks and distort the structure. And these reconstructive transformations, the volume change is significant. So what you have to do when you make a silica refractory, you have to heat treat it to get all tridymite, cristobalite, or some combination. So when you have silica refractory with tritamide or cristobalite, you still have these displacive transformations. Tritamide's a little more desirable because it's a half volume percent. Cristobalite has 2.8 volume percent, but you eliminate these reconstructive transformations because they're really huge volume changes. So if you plot expansion versus temperature, the bottom curve here is for silica glass. That's diffuse silica with very low expansion. This is quartz. Here's your displacive transformation. Cristobalite with a displacive transformation. And then tritamide has two displacive transformations. So once you get above 600 degrees C, these tend to level off. So they have very little expansion. It's not shown exactly correct on this diagram, but they're pretty flat. So once you get above 600 degrees C for silica, it has pretty good thermal shock resistance because of the pretty flat thermal expansion behavior. So this table just summarizes the phase transformations, alpha to beta 1, beta 2 tritamide. Linear expansion is 0.17, that's displacive. Alpha to beta cristobalite, it's 1% linear change, that's displacive, and alpha to beta quartz, 0.2 to maybe 0.4%, that's also displacive. And then quartz to tritamide and quartz to cristobalite are the reconstructive transformations, 5 and 6%, that's linear change, and the volume change is much higher, 14 and 17. And there's a change as is reconstructed from tritamide to cristobalite of about 1%. And then when they melt, they both expand. So this table summarizes the transformations for silica. So again, you start out with a raw material quartz, you apply heat. Tritamide is the most desired phase because it has the smallest displacive transformation, 0.5%. We usually end up with a combination of tritamide and cristobalite. They're the most desired forms because they eliminate the reconstructive transformation from quartz to tritamide or quartz to cristobalite with these large volume changes. The other ceramic or refractive material that exhibits phase transformations is zirconia, CrO2. It is one transformation from tetragonal to monoclinic zirconia. So this is the phase diagram for ZrO2. This is 100% ZrO2 on the left-hand side, and it's in mole percent. And on the right-hand side is 50 mole percent CaO. So close to 100% ZrO2, you have this phase field, monoclinic plus cubic zirconia. When you reach temperature just around 1,000 degrees C, the monoclinic transforms to tetragonal, or if you have a higher lime content, tetragonal plus cubic. So the idea here is to add enough lime to get out of the monoclinic phase field to have it all in cubic. So when you increase the temperature, it's all cubic, you eliminate the monoclinic to tetragonal phase transformation. So that occurs about 15 mole percent CaO or about 8 weight percent CaO. So tetragonal is 6.1 grams per cubic centimeter. It's denser than monoclinic, which is 5.83 grams per cubic centimeter. So when you go from tetragonal to monoclinic, or monoclinic to tetragonal, there's a density increase, so there's a volume decrease, about 2.8% in this temperature range. So if you plotted thermal expansion versus temperature, and we'll look at the solid curve, that's cycle 1. So you start out at 0, you heat it up, You have normal expansion. This is monoclinic phase is present. You, in this case, 1174 degrees C, you hit that temperature, you transform it to tetragonal, which is higher density, so there's a volume decrease. And if you keep heating it, you then have normal linear expansion. But when you cool it down at about 1048, the tetragonal transforms back to monoclinic. There's a volume expansion. And then once that transformation takes place, you have normal linear expansion. There's an offset here because you formed microcracks. So this is very disruptive to the microstructure also, this displace of transformation for zirconia. So in polycrystalline ceramics or refractories, there's thermal expansion and isotropy between the neighboring crystal grains. You have intergranular thermal stresses that develop. And when these stresses develop, if they're high enough, they'll lead to microcracking. And I already mentioned that microcracks decrease the strength, but they also dissipate stored elastic strain energy, and they improve the thermal shock resistance. So in general, a refractory that's thermal shock resistance is not going to be the strongest material. So if we have different crystals present in a refractory, and here's an example of alumina plus mullite or mullite plus silica. And this is another example, MgO plus phosphorite. They have different thermal expansions. Somehow the slide was missed here. I don't know what happened. Slide 16. Slide 16 was single crystals. You have it in your notes. It was single crystals, and we're looking at different thermal expansions in different directions in single crystals. So if you have a single crystal material, polycrystalline material, there's a random distribution of the crystals and their orientation. So you're going to have thermal expansion mismatches, which lead to microcracking. And this one shows if you have different phases present, these crystals are randomly orientated. They have different thermal expansions. So this is the thermal expansion difference between alumina and mullite, mullite and silica. So anytime delta L over L is greater than 0, you have the chance for microcracking. And I mentioned alumina and mullite and silica, MgO and phosphorite. Here's zirconia and zircon. You can see that all of these have a delta L over L greater than 0. So they'll have the potential for microcracking. And then this one here is for composite materials. So the host would be the matrix, the inclusion is the dispersed phase. So this is carbon dispersed in MgO or carbon dispersed in alumina. So this column shows which one has a larger expansion coefficient. So MgO is larger than carbon. So when you heat this material, the carbon is put in compression, and there's a volume difference. So there's a delta V over V. And whether it's in compression or tension, there's always a volume difference. So anytime that difference is greater than 0, you're going to have microcracking. And if the inclusion is in the form of a fiber, you'll have a radial difference or an axial difference, a delta R over R or a delta L over L. So in any of these cases, they're greater than 0. So in any of these composite materials, you have the potential for microcracking. I'll check the notes that were sent to you, make sure slide 16 is in there. The effect of thermal expansion and anisotropy, well, almost all heterogeneous refractory materials are susceptible to microcracking and suffer some type of microstructural damage due to this anisotropic behavior. So when you first manufacture a fired brick, you fire it at the first cooling cycle after firing, microcracks can form, and you continue thermal cycling these materials, the microcracks continue to increase in size and density. So just about all refractories are microcracked. So to measure thermal expansion, the most common way is a push rod tube dilatometer, and that measures the linear thermal expansion of a solid material. And the temperature range is minus 180 degrees C to 1,000 degrees C for a fused silica push rod tube dilatometer. So they're using fused silica low expansion material for the push rod and the tube, but it's limited to 1,000 degrees C. Higher temperatures cause the crystallite to crystallize. So an alumina push rod tube is useful to 1,600 degrees C. And if you have to go to much higher temperatures, you can use a graphite push rod and tube, and that goes to about 2,500 degrees C, but you have to use an inert atmosphere. So the lower limit in a push rod tube type dilatometer is about 0.5 times 10 to the minus 6 per degree C, which is the expansion of fused silica. So in a dilatometer, you just measure the change in length of a sample relative to that of the sample holder as a function of temperature. You have to use constant heating and cooling rates, and you calibrate with a known reference standard using constant heating and cooling rates. So the push rods and the tubes have to be stable. They have to be high temperature stable materials, and they should be made of the same material. The specimens that you use are small, so they need to be homogeneous and representative of the material. A lot of refractory materials have, of course, their aggregates on the order of a 1/4 inch. These samples are 1 to 2 inches long, maybe a 1/2 inch diameter. So sometimes that presents some issues with refractory materials, which may be coarse compared to the size of the sample. But there are other types of machines that you can use other types of samples which are much larger, especially if you have a really coarse grain refractory. So this is the definition for the coefficient of thermal expansion. It's just delta L over L0 divided by delta T. So alpha M is the mean coefficient of thermal expansion. So in a dilatometer, you're measuring thermal expansion over a temperature range. L0 is the original length at T0, and then L is the new length at the new temperature T. So this is what a dilatometer looks like. And in this case, they're showing an alumina push rod and an alumina tube. So here's your alumina push rod, and that goes inside this tube. And at the furnace, the hot end of this tube is in a furnace. The elements are represented by the circles. Here's your sample. So the sample expands as you heat it, and it moves a push rod. There's an LVDT here that records the movement and gives you the thermal expansion as a function of temperature. So the idea here is that the rod and the case heat up uniformly, and the expansion from here to the sample cancels out. And then what you actually measure is the difference between the sample and the identical length of the tube. Ideally, the rod and the holder heat up uniformly and cancel out, but that doesn't really happen in reality. So that's why you calibrate that out of the system with a calibration standard. So that's what a dilatometer looks like. And again, the holder and push rod beyond the specimen should have identical thermal gradients. And if you heat them slow enough, that tends to eliminate that radial thermal gradient. So here's an example of two types of fused silica push rod tube systems. This is a tube sitting inside a rod that's closed. There's an opening here, put the sample in. This is more of an open tube. And here's your sample again. So in either case, you're measuring the thermal expansion difference between the sample and the corresponding length of the holder. So the dilatometer measures the change in length as a function of temperature. You can measure the thermal expansion. You can also measure shrinkage during binder burnout or sintering. You can measure the transformations like for silica and zirconia. You can pick up crystallization, and you can measure the glass transition temperature, which we also talked about. So you can get a lot of information from a dilatometer trace. So that's what I have on thermal expansion. For thermal conductivity, we'll define thermal conductivity, and there's two types of conductivity we have to talk about. Photon conductivity, which is lattice vibrations, and photon conductivity, which is radiation thermal conductivity. So we'll come up with equations for each one of these types of conductivity mechanisms. And then we'll look at how the structure affects either one of these. And then we'll consider some refractory materials and how these are measured. Usually a water calorimeter or a hot wire technique. So we'll go over those two techniques. So thermal conductivity is simply the transport of heat energy through a body, and it's per unit time, per unit area, under a temperature gradient. You have to have a temperature gradient for heat transport. So the rate of heat energy transfer is determined by the thermal conductivity K and the temperature gradient dT dx. So dq dt is the amount of heat flowing normal to that area, the unit area A, in a time delta T. So the QDT, the heat flow, equals minus K, the thermal conductivity. K is considered a material constant, but it's basically a constant over a temperature range that you measure the conductivity and you have an average conductivity. But as we go through this lecture, we'll see that thermal conductivity is not constant. It's really a function of temperature. And then A is the area, T is temperature, and X is distance. So that the heat flow equals K times A dt dx. So steady state conditions, we have a constant thermal gradient. So the heat flux dq dt, we can call it small q. So here's a cube with a thermal gradient, and we'll look at this plane, actually two planes in this cube. One at x1 has a temperature T1, and one at position x2 at a temperature T2. So T1 is greater than T2. So we have a temperature gradient, so heat is going to flow from left to right. So at x1, we have qx, at x2, we have qx plus dx, which is this thickness, x2 minus x1. So we integrate between the limits of t equals t2 at x equals x2 to t equals t1 at x equals x1. So we rearrange this equation and integrate it. So q And the integral is from x1 to x2 dx over a equals minus the integral of from t1 to t2 k dt. So if we integrate that, the heat flux just equals the conductivity times the area times the temperature difference divided by the distance. Delta T is T2 minus T1, and delta X is X2 minus X1. And it assumes K is constant between these two temperatures, that delta T. There's various units for conductivity. One is watts per centimeter degree C. There's also calories per second per centimeter degree C, or BTU, inches per foot squared per hour degrees F. So depending on what units you're using, you get any one of these units for the conductivity. So I mentioned the mechanisms for heat transfer through a solid by either phonons or photons. I mean, I mentioned phonons, and we'll also add to that electrons. So heat transfer through an opaque solid, dielectric materials, those are ceramics, refractories, they're insulators, they're not electrically conductive in general. So phonons are the main mechanism for heat transfer. So these are short wave lattice vibrations. So that's the primary mechanism in a refractive material. In a metal, we have electrons. So the heat conduction by free electrons, that's the primary mechanism in a metal. If you have a semiconductor, there are a few refracting materials that are semiconductors. You have a combination of phonons and electrons that are responsible for the heat conduction. So heat conduction by shortwave lattice vibrations, the phonons at low temperatures in a semiconductor, and then as you heat the material, you generate free electrons in the semiconductor. So at higher temperatures, you increase the electrons, the conduction carriers, and you have heat flow by electrons. So heat conduction by free electrons is much more rapid than by lattice vibrations. So if we look at room temperature, we can compare copper to carbon. And carbon is a pretty high thermal conductivity refractory, but copper is still 100 times greater than carbon. And aluminum is 500 times greater than a material like sulfur. So heat conduction by free electrons is much more significant than by lattice vibrations. So we want to get an expression for phonon conduction in solids. And we'll start with a gas. So we'll use the kinetic theory of gases, derive an equation, and convert it to solids. So each one of these circles is a gas molecule. The arrows indicate the directions of movement. So when the gas molecules collide, they exchange energy. So this is the x direction. From positive x direction is from left to right. So the flux of the particles in the positive x direction is just 1/2 n Vx. So n is the concentration of particles, and Vx is their average velocity. So this is just random. There's no temperature gradient. Half the molecules are moving in the positive direction, half in the negative direction. So same flux of particles in the negative x direction, 1/2 n Vx, and n again is the concentration, and Vx is the velocity in the x direction. So now we impose a temperature gradient, which imposes an energy gradient. So the temperature versus distance. This is our temperature gradient, dt dx. At some delta T, that translates into a delta E. So this is energy versus distance. So temperature gradient gives rise to an energy gradient, dE dx. So the energy given up by a particle passing from the first region at T to, which is T plus delta T, to a region at T where the collision takes place. So it's going from a high temperature region to a lower temperature region. That energy difference, delta E, equals the heat capacity of the particle, C, times the delta T. And you can change delta T to Lx, which is the mean free path in the x direction, dt dx. T is temperature, x is the distance again. And then the mean free path, the distance between collisions, can be converted to the velocity times tau, and tau is the time between collisions. So velocity times time just equals distance. So this energy difference, it equals the heat capacity times the velocity times the time between collisions times the temperature gradient. So now the flux in the positive x direction is 1/2 n Vx, and times this term that we just derived right there, CVx tau dt dx. That's in the positive x direction. The negative x direction is the same, except we have a negative sign here. So we subtract Q minus from Q plus and get the thermal energy flux. So that's just N C Vx squared tau times our temperature gradient. So in 3 dimensions, x, y, and z, the velocity squared equals Vx squared plus Vy squared plus Vz squared. These 3 terms, Vx, Vy, and Vz, are the same. So Vx squared just equals 1/3 the average velocity squared in any direction. So the net energy flux equals 1/3 V squared NC tau dt dx. Or if we multiply N times C, C is the heat capacity for an individual gas molecule times the concentration N, that will give us the heat capacity per unit volume. So that's capital C. And phi times tau is just going to be the mean free path. So the final equation, the energy flux equals 1/3 the heat capacity, the velocity, the mean free path, times the temperature gradient. So this is the equation for heat conduction that we started out with, Q equals minus K dt dx. And this is the equation we just derived. And Q is a energy flux, and that's per unit area in time. So Q is the same here, dt dx is the same here. So K equals this term here. So K, the conductivity, equals 1/3 the heat capacity times the velocity times the mean free path. So that's for gases, but by analogy, we can write an expression for phonon conduction in solids. In the solid, atoms aren't vibrating at one frequency. There's a range of frequencies. So there's a spectrum of vibrational frequencies. So the lattice waves have a spectrum of vibration. So K equals 1/3 CVL for a gas. For a solid, K equals 1/3, and we have to integrate from 0 to omega maximum. Omega is the frequency of the lattice vibration. So there's a range of frequencies, and omega max is the maximum frequency, and heat capacity is frequency dependent. So C omega is the contribution to heat capacity for waves, lattice waves that have a frequency omega. V is the velocity, the speed of sound in the material. L is the mean free path, which is definitely frequency dependent. And then that's the omega. So that would be the expression for conductivity, phonon conductivity in a solid. So in dielectric materials, the phonon thermal conductivity is the primary mechanism, and it occurs at low, intermediate, and high temperatures. So it covers the whole temperature range. We'll talk about radiation conduction or photon conductivity in a few minutes, but that's only important at high temperatures. So the thermal conductivity is largely controlled by phonon scattering processes, and those processes are going to limit the mean free path. So this is what is really controlling the thermal conductivity, is the mean free path. And the scattering processes, phonons can interact with each other and scatter, or they can be scattered by lattice imperfections, which are impurities, intrinsic defects, grain boundaries, surfaces, pores, precipitates, any kind of lattice imperfection. So the phonon scattering processes, a phonon can react with another phonon and create a third phonon. And there's two types of reactions here. One is called an N process, and one is called a U process. So the U process is the one responsible for thermal conductivity. So in the N process, these are low energy waves, so no momentum is transferred. Phonons do not reach any type of thermal equilibrium. But for the higher energy waves, the shorter wavelength waves, momentum is transferred, energy is transferred, so phonons reach a thermal equilibrium. So for these phonon-phonon type of interactions, if we consider just the low temperatures, so these are phonons with wave numbers large enough for U process collisions. So these are short wavelengths, and they're going to vary exponentially with temperature. So the mean free path is proportional to E to this constant, which is the Debye characteristic temperature divided by 2T, and therefore K is just proportional to the same thing, E to the Debye constant divided by 2T. So this Debye characteristic temperature is a temperature that gives the highest mode of vibration. So that's Planck's constant times omega max, the maximum frequency of a lattice vibration, divided by K, which is Boltzmann's constant. So there's an exponential decrease at very low temperatures as the temperature is increased, an exponential decrease in the conductivity and the mean free path. So at high temperatures, we have phonons with large wave numbers, short wavelengths, so they increase linearly with temperature. So now a large portion of the phonon collisions are this U-type. So at higher temperatures, the mean free path is now proportional to 1 over the temperature, and K is also proportional to 1 over temperature. So this is how conductivity falls off with temperature in a 1 over T relationship. So phonon-phonon interactions are U processes, and then structural imperfections. I mentioned impurities, intrinsic defects, grain boundaries, surfaces, pores, precipitates. Imperfections will scatter these lattice waves. If the phonon wavelength is less than the imperfection size. So imperfections will not act as scattering sites if the phonon wavelength is greater than the imperfection size. In that case, the phonon sees a continuous structure and it's not scattered at all. So what this means is we can illustrate this for a single crystal of alumina. So this is thermal conductivity versus temperature, and this is in degrees K, and this is the calories second per degree centimeter, degree C, and centimeter squared. So 0 degrees C, region 1 is just above 0 degrees C. Region 2 is still at low temperatures. Region 3 is intermediate temperatures. Region 4 is higher temperatures, and region 5 is even higher temperatures. So we'll go over each one of these regions and note that our Dubai temperature in this case is about 500 degrees K. So region 1 is very low temperatures, less than 10 degrees K, just above 0 degrees K. So the phonon mean free path is quite large at very low temperatures. It's the same magnitude as the sample size. So these are on the order of centimeters. So boundary effects dominate. So the sample size boundaries dominate. U processes are ineffective. They place at these low temperatures. So now the conductivity is proportional to the heat capacity, which is a function of omega, the velocity, and then the sample dimensions instead of the mean free path. So D is the sample size. So at very low temperatures, the heat capacity is proportional to T cubed. So as the temperature decreases, the heat capacity falls off. So the heat capacity falls to 0 at 0 degrees K. So because the heat capacity falls off, the conductivity at these low temperatures falls off to 0 at 0 degrees K. So region 2 is low temperatures greater than 10 degrees K. That's where you have U processes leading to this type of relationship where conductivity is proportional to E to the Debye constant divided by 2T. So that's a pretty rapid drop in the conductivity. And then region 3 is intermediate temperatures. Their U processes are taking place. That's where the conductivity falls off as 1 over T. So this is a 1 over T relationship. This is the exponential relationship. And then in region 4, now the phonons are very short wavelength. So the lattice spacing is going to determine the thermal conductivity because of scattering taking place by the lattice. So now the mean free path is approximately equal to the lattice spacing, and phi is a constant, and the heat capacity at high temperatures above room temperature is essentially constant. So now conductivity is no longer a function of temperature, it's a function of the mean free path and the lattice spacing, so K is constant. So if we go back to our diagram here, you're seeing in this higher temperature region, the conductivity tends to be flat. It's not a function of temperature. And then in region 5, if the material has some transparency, radiation conductivity can take place. Or if the material has pores, you can have radiation across pores. So region 5 depends on the transparency of the material and the pore volume. So there may be a little bit of an upswing in conductivity due to the photon or radiation conduction taking place. So we're primarily interested in this region here, part of region 2, 3, 4, and 5. So I mentioned that conductivity is considered a material constant, but it's over a temperature range. Obviously, you can see here, conductivity is a function of temperature. So we'll look at how the structure affects the conductivity. So the structural aspects that affect thermal conductivity. If the structure becomes more complex, um, that lowers the mean free path. So the more complex the structure, the lower the mean free path. And as L omega decreases, that lowers the conductivity. So here's some refractory materials, MgO, Al2O3, spinel, and phosphorite. So as these materials become more complex, the crystal structure becomes more complex, the mean free path goes down, and the conductivity goes down. So MgO and alumina are very high conductivity materials for refractories. So atomic weight differences. So as the atomic weight differences increase, that lowers the mean free path and that lowers the conductivity. So this is thermal conductivity versus atomic weight of the metal cation. So the bottom curve here is for metal oxide. So this would be MgO, Al2O3, BeO, and so on. The top curve is for carbides, such as carbon, silicon carbide, titanium carbide. And the conductivity is here in the BTU units. But as the atomic weight increases of the cation, the conductivity decreases. Beryllium oxide is very high conductivity material. And then still MgO and alumina are still pretty high conductivity refractories. Grain boundaries, they scatter photons only when the grain size approaches the mean free path. So mean free paths close to absolute zero are quite large, but at a room temperature, high temperatures, they're pretty small. So at room temperature, the mean free path may only be 100 angstroms. At high temperatures, it may only be 5 or 10 angstroms. So coarse grain refractories are not, you don't see grains this small. So grain boundaries are not going to scatter the photons. So grain boundary effects are not important at ordinary temperatures because the crystal size is not small enough for scattering. So here's some typical thermal conductivity versus temperature. This is a single crystal of alumina, and then the other curve is polycrystal alumina. The single crystal happens to be transparent, so there's some photon or radiation conduction giving this deviation here. But they start out pretty close because there's no grain boundary scattering. There's only a difference because of radiation effects taking place. So if this were not transparent, these curves would be the same, single crystal versus polycrystal. And there's an example here for TiO2 and calcium fluoride. So grain boundary scattering is not important. And then another aspect is solid solution. So when you have a solid solution, you have mass differences, size differences, elastic strain fields are created, you have bonding differences. All of that leads to a lower mean free path, again, which lowers conductivity. So here's thermal conductivity, and these are the units based on calories versus the composition here. So this is 100% MgO on the left-hand side. This is 100% NiO on the right-hand side. MgO and NiO form a complete solid solution, so they completely dissolve in each other. So at 100% MgO, you have the highest thermal conductivities, and at 100% NiO, you have the highest thermal conductivities for the pure end members. So there's a curve for 200, and for 1,000. And note that the curve for 1,000 is lower because the conductivity is lower at the higher temperature. It decreases with temperature. But in the middle of this diagram is a minimum. So the solid solution is lowering the thermal conductivity. There are quite a few refractories that have solid solution. Some complete solid solutions, some partial solid solutions. Another one of the aspects that I want to mention is for glasses. Glasses are disordered structures. They're not well-ordered crystalline structures, so they're going to have poor thermal conductivity. So compared to crystals, glasses have lower thermal conductivity. And in most refractories, there's some glass phase present, and in some of the fire clear refractories, there's a significant amount of glass present. So this is thermal conductivity versus temperature. And the top curve here is for quartz. And then if you take that quartz and you make fused quartz, the fused silica, the amorphous material, you can see the drop in the thermal conductivity from quartz to the glassy version, fused quartz. So L omega for fused quartz is limited by the size of the SiO2 tetrahedra. And these are on the order of 8 angstroms. So since the glass structure is random, K tends to be a constant above the Debye temperature, and then below the Debye temperature, it's going to decrease because of the heat capacity decreasing. You can see the Debye temperature is probably in this range here. It starts to level off as a function of temperature. So in general, glasses have low thermal conductivity. So if they're a component in your refractory, they're going to lower the conductivity. So factors that favor high thermal conductivity, strong atomic bonding, small atomic weight components, small atomic weight differences between the different atoms, simple crystal structures, a small number of components, high purity, and high purity means small concentration of solute ions, impurities, and other crystallographic defects. Factors that affect low thermal conductivity would be grain boundaries, second phases, porosity and microcracks have a big effect, and the presence of glass and other non-crystalline phases. So we'll get started and we'll define radiation conductivity, and we'll probably stop there. So electromagnetic radiation transmission by transparent materials at high temperatures. So thermal radiation is produced at high temperatures. So at very high temperatures, electrons are excited. They go to increased energy states. And then when they decay back to their normal energy states, they release thermal radiation. So that difference in energy is released as photons. And the radiation that we're interested in, the wavelengths are between 0.1 and 100 microns. So 0.1 micron is the lower wavelength of the ultraviolet spectrum. 1 micron is the center of the visible spectrum, and 100 microns are the shorter wavelengths of the infrared spectrum. So this is the radiation spectrum, and we're interested in this area here. Here's the visible, the ultraviolet, and then the infrared. So we're somewhere in the infrared region through the visible to the edge of the ultraviolet region. So this is an equation that we can write for electromagnetic radiation. And this is transmission by transparent materials at high temperatures. Refractory materials are opaque. So this really doesn't apply because they're not transparent, but we'll derive the equation for transparent materials. And then what's important in refractory materials is pores, because you can have thermal radiation across pores. So we'll alter that equation to account for porosity and develop another equation for radiation in refractory materials when there's porosity present. And just about every refractory material, unless it's fused cast, has 10 to 20% porosity. So photon conduction is similar to phonon conduction. So here's our basic equation for lattice wave conduction or phonon conduction. K equals 1/3 C, the heat capacity times the velocity times the mean free path. So we'll derive a similar equation for photon conduction. So we start out with the total energy per unit volume for black body radiation. So that's E radiation equals 4 times sigma. Sigma is a constant, the Stefan-Boltzmann constant. N cubed, N is the refractive index. T to the 4th power, T is temperature. And then C is the velocity of light. So T to the 4th power, as the temperature increases, the radiation increases rapidly because T is to the 4th power. So here's the equation I just showed. E radiation equals 4. Sigma is a constant, N is the refractive index cubed, T is temperature, and C is another constant. So the derivative of E with respect to T is the heat capacity. So C radiation equals the E radiation dt, and now this becomes 16 sigma N cubed T cubed over C. The velocity of the radiation V equals C over N. C is the speed of light, and N is the refractive index. So we substitute into this equation for C and V, and we end up with an equation for K radiation, 1/3 16 sigma N cubed T cubed divided by C, and that's times C over N times the mean free path of the radiation. And that simplifies to 1/3 16 sigma N squared T cubed times the radiation mean free path. You can also replace L by 1 over A. A is the absorption coefficient. So the higher the absorption coefficient A, the lower the mean free path. So you can write it in terms of 1 over A instead of L. So that's the basic equation for radiation conduction in a transparent material. So what's really controlling the radiation here, well, to a large extent, is the mean free path. So this mean free path, which equals 1 over the absorption coefficient, is both frequency and temperature dependent. So what processes produce absorption and lower the mean free path? Well, in the ultraviolet region, radiation absorption is due to electronic excitation. In the infrared region, absorption is due to lattice excitation. So that has to do with the resonant frequencies of the atomic bonds. And then in the optical or visible region, dielectric materials like ceramics or refractories are usually transparent to the radiation. So there's no absorption. So sometimes if you have transition elements present, you may have some absorption due to electronic excitation. So if you plotted absorption versus wavelength, and these are different transparent materials, window glass, a glass doped with a little iron oxide, Vicor glass, fused silica, and then you have a couple single crystals, alumina and alumina doped with chrome. So here's your ultraviolet region, your visible region, and your infrared region starts here. So you can see the absorption edge increases in the ultraviolet region. And then when you get into the infrared region, all these absorption curves are going upward. So that the minimum in the absorption occurs in the visible region. So that's the wavelength dependence. So the temperature dependence looks something like this. These are typical mean free paths for some transparent materials as a function of temperature. So mean free path versus temperature, different single crystals in glasses. You can see that the mean free path is increasing with increasing temperature. And then if you take some of these same materials and you add porosity, that really scatters radiation. So it really lowers the mean free path as you add porosity in a transparent material. So the energy transfer really depends on the mean free path L radiation. So opaque materials such as a refractory, the mean free path is zero. There's no contribution to K radiation. If you have a transparent material, you have two possibilities. So the first possibility, the mean free path is small compared to the size of the sample. So when you have a small mean free path, energy transfer takes place by photon conduction. But in the second possibility, if the radiation is large compared to the size of the sample, the radiation just passes through the sample. There's very little interaction. And any energy transfer that takes place is controlled by the boundaries. So case 2 really applies to pores in refractory materials or ceramic materials. So possibility 1, materials are not sensitive to the boundaries. The mean free path of the radiation is much smaller than a sample size D. So K radiation becomes a material constant. Photons are absorbed and re-radiated. You have a temperature gradient, and that's going to lead to heat flow. So this is the equation we derive for K radiation in a transparent material. That applies to this case where the mean free path is smaller than the sample size. So the other case where we have boundary effects, so now the mean free path is much larger than the sample size. So here's a material of dimension D with two boundaries, and the mean free path of the radiation is much larger. It will pass through this material. So energy is not absorbed or re-radiated in this material. So K is no longer a material constant. So in the second possibility, you have transfer without any interaction when the radiation mean free path is larger than the sample size. But what you do is you alter the photon or radiation velocity. So V equals C over N. Again, C is the velocity of light, N is the refractive index. So N is going to be a number greater than 1, so it's going to lower the velocity. So boundary effects are important because the photon mean free paths for ceramic materials are usually between 0.1 and 10 centimeters. So the mean free path is similar to the sample sizes. So if we have a material of thickness D, an area A on each of these boundaries, boundary 1 has an emissivity 1 and a temperature 1. Boundary 2 has an emissivity 2 and a temperature 2. We can write this equation for the heat transfer between the two boundaries. And the net heat flow equals N squared, the refractive index squared, a constant, the Stefan-Boltzmann constant sigma, the area, and the temperature to the fourth power minus the temperature to the fourth power for T1 and T2 And then our emissivities, it's 1 over, then 1 over epsilon 1 plus 1 over epsilon 2 minus 1. So we make some assumptions to make this equation simpler. Epsilon 1 and epsilon 2 are equal. So that becomes epsilon over 2 minus epsilon. We'll just call it epsilon effective. So this equation I just showed for Q net becomes this equation here, n squared sigma a, T1 to the fourth power minus T2 to the fourth power, and our effective emissivity. And then if we say the temperatures are approximately equal, we can expand this term, T1 to the fourth power minus T2 to the fourth power, and as follows, T1 minus T2, T1 plus T2, and then T1 squared plus T2 squared. So T1 minus T2 is just delta T. T1 plus T2 is just 2T. And then T1 squared plus T2 squared is just 2T squared. So that this term here, T1 to the fourth power minus T2 to the fourth power, just equals 4T cubed delta T. Putting that into our equation, Q just equals 4n squared sigma A epsilon effective T cubed times delta T. So Q over A equals K, we'll call it K boundary, delta T, delta X. Solve for K boundary, that's Q over A, delta T, delta X over delta T. And in our case here, for the material has thickness D, delta X equals D. So K boundary just equals Q over A, D over delta T. And we substitute for Q. So we get this equation and we simplify it. So the boundary, K boundary equals 4n squared sigma epsilon effective T cubed times D. So now this is the thermal conductivity between boundaries with a non-absorbing material in between. So this could be a pore with air in between, air in the pore, and the pore diameter sets our boundaries. So we take our two equations, we derive K boundary and K radiation. This is K boundary, this is K radiation, and we simplify them. We just get 3/4 D over L radiation, our emissivity divided by 2 minus the emissivity, and that equals P, that ratio. So if P is less than 1, where we have large mean free paths, it turns out K boundary is only a fraction of K radiation. So I'm just showing that the conductivity due to the boundary effects is much smaller than the true K radiation conductivity. So K boundary is determined by the geometry and boundaries. K radiation is a material property. So I think this will be the last slide here. Opaque materials with pores, that's the refractory. Like I said, most refractories have up to 20 or more percent porosity. So at our higher temperatures, the mean free path is going to be much greater than the pore size. So this is the equation we had, and we're putting in D, the pore diameter, instead of the mean free path. So the effective radiation between pore surfaces is given by this equation, and dP is the pore diameter. So if you're trying to design a material with low thermal conductivity and insulation type material, you want this pore size to be small. So it becomes a barrier to thermal conductivity by radiation. If this number, if the pore size is large, that's going to increase the conductivity due to radiation. So this equation is useful for designing materials with high or low thermal conductivity. So that's a good place to stop. We'll finish up conductivity, next class, and then we'll move on to fracture, uh, brittle fracture behavior. And then once we finish that, we'll spend a couple lectures going over the thermal conductivity theories, which are going to tie together uh, thermal expansion, thermal conductivity, elasticity, and fracture. So again, if you have any questions, let me know, and I will see you next Thursday, and I will check what happened to that missing slide, and I'll make sure I'll include it in the lecture on Thursday and just go over that very briefly. Again, thanks for attending, and I'll see you on Thursday.